Alright, so the first thing we're going to do is we're going to allocate the space for in the global stiffness matrix. So we need a constant array. That's how big? 8 by 8. Okay. Now let's write that connectivity array like we did. So 1, 2, 4, 4, 3, 1. Okay. But we also have this correspondence, so I'm going to call that core. All right, and I'm going to use a table to generate it for me. And after I generate the table, I think you'll see what I did. It's pretty clear. Okay, so I said create a table that is a nested list that contains I and I plus 1, where I goes from 1 to the length of k, which is 8, in steps of 2. So it goes 1, 3, 5, 7. Okay, and what that does is, okay, so there's 4 nodes. Each of these nested lists corresponds to the node. So this is node 1, node 2, node 3, and node 4. Okay? Each of them have 2 degrees of freedom. So node 1 has degree of freedom D1, D2. Node 2 has degree of freedom D3, D4. Node 3 has degree of freedom D5, D6. Node 4, D7, D8. Okay? So what we can do then is if we say core connect, so I'm going to take the connectivity of the first element, which is this, right? 1, 2, 4. I get this, and then I want to flatten that. So I'm just going to get rid of the... Alright. So what this means is that the connectivity in the first element corresponds to node number 1, 2, and 4, but degree of freedom 1, 2, 3, 4, 7, and 8. Because each node has 2 degrees of freedom. Okay. So anyway, you know, I'm not sure if you guys, I see a lot of blank looks, but anyway, let me just move on, and then we can, so I can finish the screencast, and we'll talk a little bit more, help you try to understand, right? So one thing I can do, I can just call that position, meaning like position in the global stiffness matrix. And then I can do this. I can say do so here's where I'm actually going to perform the assembly. Oh, it got messed up because there's a matrix form somewhere right here. So here's my global stiffness matrix. All right, and it's bigger than what you can see there, but it's 8 down. You can see all the rows, but then it goes a little bit off the screen there. Right. So that's the global, you know, assembled stiffness matrix. So then what we'll do, we'll nodes 1 and node 3 are fixed. They're 0, right? So that means that D1 and D2 are 0, and 3 corresponds to, if this is 1, this is 2, this is 3. So D5 and D6 are 0. So what that means is I need to drop the 5th and 6th row and the 1st and 2nd row from the global stiffness matrix in order to solve this. So this is how you applying the boundary conditions. Okay, so I'll go ahead and do that. Let's say K new equals drop K 5 6 transpose 5 6 transpose 1 2 transpose 1 2. I need drop, drop, drop. All right, so there's K new. We'll go ahead and plug in the numbers just to finish this problem. But so A is 120, B 160, HE 0.036, EY 30 times 10 to the 6th, new 0.25. So we get that. So then we could actually solve this. I'm just we're gonna solve K new, and we don't have time to go through evaluating the pressure on the side, but that's the same we've always done. You can just evaluate that over a line segment, and that's going to distribute the force from due to that distributed load to the nodes 2 and 4. And so let me just take a sneak peek. I think it's 800 0 800 0. So 800 0 800 0. That's what the force vector would look like had we had time to calculate it, and so we can solve for that. So those are the displacements in the x and y direction at each of those nodes.